Good morning, everyone. We're going to start this talk from Gerolf Hoflehner from Apple about performances and Headroom.
Okay, thank you. So I'm Gerolf. I will talk about performance improvements from last year and Headroom. So I have four messages in this talk. We push performance, and we will continue to push performance by doing essentially four things. By tuning and being focused on local optimization, by adding new optimization capabilities, either by adding new optimizations or by expanding the capabilities of existing optimizations, by getting inspired by heroic optimizations, and also by finding ways to expose all this great work we are doing on benchmarks to get it to the developer, and hopefully this way to get it to a wide range of applications. So where do I come from? The benchmarks we look at are Spec 2006 integer benchmarks, some kernels, the LLVM test suite, and the 7 C++ benchmarks from the floating point benchmark suite in Spec. My setup is the compiler from last year, Clang 600 versus Clang 700. So they roughly correspond to LLVM 3.5 and LLVM 3.7. So the performance numbers here are really an Apple-centric view at this point, because not all our changes are committed to open source yet, but they will be. So you cannot quite reproduce the numbers yet, but you will be able to do so soon. The options, you will see the gains are 03 FLTO PGO and as well 03 FLTO, and most of the gains are actually in 03, and all the measurements are happening on ARM64. So what gains do we have? On the Spec 2006 integer suite since last year, we see in the geomean an improvement by 6.5%, and on kernels, we see improvements by up to 70%. And this is to my heroes who made all these numbers possible. So it's some of the many brilliant minds in this community. Thanks to them. Now let's dive into the detailed numbers. Here you see on the x-axis the 12 Spec 2006 integer benchmarks. On the y-axis are the relative gains compared to last year. The takeaway from the slide is that almost all benchmarks improve nicely. They all see some single-digit gains. The number of outliers. So first, the numbers are real because we also have a challenge we need to work on next year with Omnet PP, a benchmark that did not quite move in the direction we wanted, and also nice gains on Xilinx and on Hammer. Xilinx is in a way less interesting because it's an outlier compared to the others, and more interesting will be the gains in Hammer, and I will talk about all of them in the next slide. So some of the reasons for the gains are, some of you will recognize this pattern. It's the alpha macro in Perl, where we managed to do some clever numerical manipulations to eliminate 2 out of the 4 compares. Better instruction selection by combining a compare and branch to a test bit not 0 gives some gains in MCF, as did the load store combining optimization there. Unrolling of loops with conditional store enabled vectorization in a hot loop in libquantum. And here's the Xilinx BMK case, where we essentially tuned loop rotation to be register pressure aware and saw an amazing gain, which we did not expect. What was happening there is that there is a use of an induction variable outside the loop. It's a multi-exit loop. The induction variable gets hoisted into a latch, increases the register pressure, and that case has been tuned, giving us the gain. The common thread I want to stress in all of this is these are many optimizations. They're fairly narrow. They tune on heuristic or improve an expression, things like that. The case is completely different for Hammer. On Hammer, it's a benchmark, a gene sequencing benchmark, where all the time is spent in a single hot loop. And there we had to do something more clever than just tuning. So we came up with splitting this huge loop. I only show a piece of it, and I will illustrate what is happening. We split the loop into parts, and this is loop distribution. And the benefits we get from loop distribution is essentially twofold. It changes the memory access pattern, and we get better cache associativity. And in the case of Hammer, since we partition the loop into smaller pieces, pieces of the loop become vectorizable. So in this case, the first loop in Hammer becomes vectorizable. And because we do distribution and have a smaller loop, we also have better dependence information. So in the second part of the loop, we could apply a different optimization, where we could apply a store-to-load forwarding that essentially eliminates a load on the hot path and helps us to reduce the critical path length in the second loop. And this is done when you look at the bottom loop and you look at the accesses to dk and dk minus 1, what you will see there, it's a loop carried dependence. And if we have the proper dependence information, we can forward that store in one iteration to the load in the other, and we do this by introducing a temporary for the accesses to dk. It's one temporary. It also has to be initialized. You can trust me that this transformation is correct, and you will learn a lot more about this in a great talk Adam will give later this afternoon. And with that, I move on to reflect on what we have done. As I stressed before, we get the gains from lots of small optimizations, but also thinking about what new optimizations we can apply. And in this case, we added loop distribution and advanced the capabilities of the loop transformation framework. And with that, I move on to kernel performance. I look at 5 kernels here on the x-axis. Quite familiar ones, some encryption, some Sobel filter, compress. What you see there is actually initially we saw regressions, and I will talk about that in the next slide, where they come from and what we can do about it. And also big gains on some of them. The gain in Black-Scholes comes from enabling loops with math intrinsics like the trigonometric functions, a logarithm, exponential to get vectorized. And I will discuss in more detail now where this gain of up to 70% comes from for convolution loop. And this, again, is just a snippet of a convolution loop to explain the concept that's behind here. The big idea is to come up with better estimates when we should unroll loops. What we're really seeing here in the code is actually a loop nest, and it would get fairly big when the loop nest gets unrolled. And traditionally, the unroller would not do this. But what we found is that a lot of data, a lot of input into the loop become constant as we unroll the loop and look at the iterations one at a time. And that is due to a static array that consists only of constants. And that enables us essentially to simulate the loop and replace the array accesses of k in this example with the constants from the array. And when we do this, we find that we can simplify many expressions, so loop unrolling becomes much more attractive, and we can eliminate a number of expensive operations. In the first case, multiply by null is idempotent, so it saves the multiply and add all together. In the case of a 1, we save the multiply, and so on and so forth. And that concept of simulating loop expands the capabilities of the loop unroller. And again, this is just an appetizer, and later this afternoon you will hear a great talk about this in much more detail by Michael. As I said, we also have regressions, and it's very well worth to look into where they are coming from. So in the case of the encryption benchmark, what happened is that better alias analysis was made available to the scheduler, which resulted in aggressive load hoisting. So loads got hoisted across stores within the scheduling region, and that resulted in the extra register pressure and all the things that come out of that. What we found is that it's enough to keep the source code ordering of the memory instructions and let the out-of-order engine do the hard work. There has been a lot of tuning going on and investigation that this is the right thing to do, and just recently Matthias completed that work and committed that change to the trunk. In the Sobel filter, it's a little bit different. There was a normalization of the LSR expressions, and they resulted essentially into different expressions for base addresses of two-dimensional arrays, or in general, multi-dimensional arrays. So when you have accesses to the same, multiple accesses to the same array, we recompute the base address for this reason multiple times. And the fix for this is a patch in CodeGen Prepare where we normalize the expressions so that instead of a gap, we're using an add, and that enables CSE to recognize that the base addresses in all these accesses are identical, and we will get back that performance. Compress is a little bit more tricky. So we combine or compare and branch to a test bit not 0, and what happens is it disables the conditional compare optimization. So that is not being fixed yet, because by looking into this, we found that this optimization, the conditional compare optimization, is actually quite tricky. And the compiler needs to be very careful about it, because once you combine two branches, what can happen is that you transfer a branch mispredict information to the combined branch. So the combined branch may actually behave much worse with respect to misprediction ratio than the separate branches. And so the compiler needs to be very careful and about when to apply this optimization, and need to check whether it has enough information to do it, to make it a win. So that is still work in progress. And with that, let's see what all these work on the kernels and spec did on the LLVM test suite. This is completely in the eye of the beholder. When I look at it, the red part to me means we still have some losses, some development debt, which we need to look at. Some of it I understand, as I explained, from the regressions in the kernel, but I don't think all. When I ask other people, they tell me that the green bars, they're really real, they're gains, and the red part, that's just noise. All right, so we discussed all the gains and all the good work we did last year, and hopefully everybody will benefit in their performance work from it. Now let's look at some headroom. And what I'm doing here is I look at the spec benchmark suites, both the integer and the floating point, and I try to characterize where the gains could come from. So I have 4 categories: tuning, advanced, heroic, and unknown. I put random numbers on tuning because from past experience, we always find about 2% performance somewhere. And the unknown is completely a wild guess. But advanced and heroic, I think we know what can be done. So 2% from tuning, 10% from an array of structure to structure of array optimization, which we'll discuss soon. There's even more gain from being really heroic, and there's probably some more as we start looking more into what we can do with profiling optimizations and so on and so forth. And a similar picture for the Spec 2006 floating point benchmark, again, just the 7 C++ benchmarks, same categories. As I said, always 2% from tuning. The advanced case is interesting. There's also a case for array of structure to structure of array, so that makes it worth looking into that, and hopefully soon we will get a nice gain from the work on the open source community from value profiling in the ray tracing benchmark. And of course, there's always some headroom, which we don't know yet. Okay, array of structs to structs of array. Why is this beneficial for 2 benchmarks, one on the floating point, one on the integer suite? So it's libquantum, that's the setup. You have an array with a pointer to a node, and that node points to a structure that consists of 2 elements, a complex field amplitude and an integer state. And you have a field, you have a hot loop that only accesses some of the data, but not all. So here's what it looks like. I tried to illustrate the array of structures. It structures with this complex field and the integer field with these red and blue boxes. So you see the first structure element consisting of the first 2 red bars and the blue bar, and so on and so forth. And below you see the sample loop, so what is going on. Again, free structure elements. At the bottom you see the cache. It's a fictitious cache line size, just to illustrate the accesses and what is happening in the benchmark. So we load the first state element of the first structure, and our cache is 8-byte aligned. The fields are 4-byte aligned. So here's our cache line, which has to be 8-byte aligned when we access the data. We load the data into the cache. The state field in the second structure element is not 8-byte aligned, so we have to align the address to 8-byte and get the data into the cache line. And the same for the next structure element, and so on and so forth. And what you see is, although we only access some data in the loop, we bring in a lot of data into the cache, which we don't use. And the way to avoid this is by splitting the structure into smaller components, so the fields of the original structure essentially become arrays themselves. And when we do this, we get much better locality in the data. And when we actually load the data, we have to change, of course, all the accesses to the original node structure, because now we don't access the field, but the array element in a field. And when we do all this and load the data in the loop, you see that there's no data wasted. All the data brought into the cache are actually used. So the takeaway is the reason why people look into this transformation is because it speeds up benchmarks in applications that are memory bandwidth bound and or cache bound. It's not free. It comes with a huge challenge. You have to make sure that you get the locality right. So it casts to from the structure. You have to check which types escape. Are the addresses taken of the individual fields? You have to look at all the parameter and return addresses. You have to think about the semantic of constants. You have to do all the transformation to make it happening. So all the data accesses, as I said, the original fields become arrays. You have to make sure that you get all the accesses right. You have to know all the memory allocation sites to make sure that the memory is allocated correctly. And if you think about productizing this, you probably also want to think about the usability. In the debugger, you probably want to keep the original view of the source code. So quite briefly, a few thoughts about these challenges. As I said, the original field elements become arrays, and all the accesses have to be adjusted accordingly. And the case of constants is more interesting. So when you take a size of the original structure in the LLVM RR code, you only see a constant. And when you want to reason about these constants, so they can be passed as constants in memory allocation routines. They can be anywhere in the function. These constants can be anywhere in the code. And we need to find a way to communicate to the compiler that this constant is actually associated with the type, with the original structure type, and to do the proper things and adjust the constants accordingly. And of course, parameter passing, when there is a pointer passed to the original structure, can we actually pass pointers to all the individual structures that we have split. And so lots of investigation, lots of things to consider. I think I convinced you that it is a very brittle optimization. It certainly works well in a benchmark setting when you know the pattern you're looking for. It's also a very valuable optimization, and many people have looked into this. So this goes back into the time that libquantum came out. People started thinking about this. So our compilers, Open64, GCC, HP compiler, Intel compiler, they all have that information, that optimization in some form. And last year, Prashant presented an implementation of these kind of ideas at the LLVM developer conference, but none of this code has been committed. So I think there's a lot of opportunity if we find ways to communicate with the user to actually apply this transformation. And this is something we should think about as we move forward. There's more headroom. And what I tell you now is really top secret. So this cannot leave the room or the community. So there's a guy out there that actually works on something we usually don't work on. It's on compiler heroics. And let's see what he's doing. Oh, once you look under the rug, there are many more. All right. So let's see which companies they're working for. Oh, don't tell. Okay. So let's just see what's going on. So libquantum is really the motherlode for benchmark hacking. And the reason that's the case is because it's basically a crippled benchmark, where some of the functionality has been turned off, and the compiler with a whole program view can figure it out. The scenario is that you have back-to-back calls with hot loops inside them, and you can find when you know what to do, and when the compiler knows at the right time what to do, it can figure out that it can fuse these loops. So some ingredients are whole program visibility, alias analysis, global mod ref, and a number of other transformations, and you have to apply the proper cost model. So teach the compiler to find the benchmark pattern, and then you get inline infusion and get really great gains. So how is this done? So the setup is two functions that are fairly similar called back-to-back. The structure is quite simple. You have a call at the beginning of both functions and a simple if-then-else structure. The important loops are hidden in the else block in both cases, and the else block is wrapped in a call before and a call after. So now let's look at it bottom up, what's going on there. Let's first start at looking at deco here. So what's going on in that function? It is checking a global variable, then does something, and then returns. Now with global value prop, the compiler can figure out that this global variable is 0 in all the cases. So essentially this means that we are dealing with a dead function call in the end and can eliminate it. So now let's move on and look at the first function call. Again, it's relatively simple. All it does, it returns the value of a global variable. So we can simply inline that function and check for the global variable. Now things become much simpler in both cases. And now we can start thinking about inlining both functions. And what we find with global modref is that this global variable is independent of what is happening in the else block in both cases. So now we can start combining them and keep the program order. So we check for the global variable, execute the block from the first function, the then block from the first function, then the then block from the second function. And more interesting is the else case. So we have similar structure in both cases, a call, then the loop, and another call, and the loop. With global modref, we can figure out that the loop is independent, that the variables in the loop are not touched and not modified by the function call, and we can hoist the call above the loop, and now we have the loop where we want them close to each other. It's a tricky beast. When we hoist the load and in general control structures above loops, we have to be very careful that we can get it correct. The way you see the code on the slide is, of course, incorrect when you think of preserving the program order without inlining and with inlining, because we would return after the first function call. But in program order, we have to make sure we execute both. And it works out nicely in this case because the compiler, in all its magic, can figure out that the call to foo always returns true or always returns false. And so we can make sure that we execute both by simply introducing variables. And now, after we have guaranteed correctness of the program flow, we are ready to apply the magic, fuse the two loops, which have the same loop boundaries, of course. And now, instead of traversing the loop twice, we only traverse it once. And this was just one instance of what can happen in that benchmark. And we have a really big bagger happening. So what can we learn from this? It's, of course, one thing to say, OK, it's heroic, forget about it. Who cares? Would never happen in a real-world scenario. But I think what is interesting about this case is that the optimizations, the ingredients you need to eventually make that heroic optimization happening can actually lead you and guide you to what techniques you want to implement in the compiler so that you improve your general optimization arsenal and get improvements on not just one benchmark, but hopefully on many other applications. So what is unique here is that the optimization scope is a call chain. And that's interesting. It's something you probably want to do anyway. So you can think of, just forget fusion and on all this other stuff, but look at a call chain and maybe just allocate the stack at one time at the beginning of the chain, or allocate registers across the call chain interprocedurally. So it is an interesting idea that can help in other cases. As I said, it's back-to-back calls in this case. Both functions are similar. What does it mean for two functions to be similar? Can we exploit a concept of function similarity in other contexts, like code size optimizations, where we merge functions that are similar? Of course, there's a challenge. When is it safe to hoist statements across loops? So even in the intraprocedural case, once we support loop fusion in general, it's a problem we need to think about. It just happens to show up in this heroic case. But it's also interesting in the intraprocedural setup. So, and finally, loop fusion itself. It's a useful technique. If you want to make this heroic effort happen, it's one of the ingredients you need. And I think it's an interesting technique in general. Like loop distribution, it would advance the capability of our loop transformation framework. So the takeaways are really, when you break down a heroic effort, you can learn quite a bit from it. And the techniques needed for it can help to generalize and advance the optimization technology we have in the compiler. But what we need to be very careful about is the cost model. When do we want the compiler to do this? And I think the opportunity we have is to think about ways to let the compiler, or to make the compiler communicate better to the user when there is potential to exploit some of these opportunities. But the compiler needs to ask for more information. And this is in the very baby steps of thought at this point. But I want to share two ideas or some work that has been done in that direction to give you the idea. So it's basically, for example, instruct the compiler to look for an array of structure to structure of array transformation when it is known that an application is memory bound, or to have a mode in the compiler to figure out optimizations it could do and inform the user that with a little bit of information, for example, in the AOS to SOA case, if you didn't do that cast, or if you told me about this constant, then I could do that optimization. So we can think along these lines. And to feed these thoughts, I have two examples on how we can expose performance opportunities to developers. One of them is by a built-in. So a recent example is the built-in for non-temporal stores. The scenario is you have a streaming loop, you have no temporal reuse, and in that scenario, we don't need to the processor doesn't need to bring in the data into the cache. It can result in a lot of saving for streaming loops, and the developer can apply the built-in and get nice gains from it. But the compiler could also apply it. It has to make sure that the alignments are right. It has to make sure that the alias information is right. And if that information is not there, it could report back to the user, can you tell me whether or not these two array elements alias? And to do so, you can apply the restrict keyword and so on and so forth. And where we have actually done something like this, as I said, as a very first step towards that, was Tyler's work this summer with the vectorizer. So it's a little bit different setup, but it's the same idea. So it's a really key optimization in the compiler, which in many cases fires and gives good gains, but in some cases it cannot. And it cannot for a number of reasons. It may have to commute floating point values, which is not always safe, or it does not have enough information about aliases, and there's a threshold in the compiler where it can only issue a certain number of memory checks to get dynamic information about whether or not two data elements alias. And in this case, the compiler can now report back to the developer, hey, could really vectorize this loop, but I need a little bit more information. If you know that in this case, in the example you see on the slide, if the array elements are independent, just tell me about it. And what is important, it's not just the compiler reporting back, hey, I know something, and you developer figure it out, but it's really very concise information where the compiler says, I not only know something, but this is the very specific thing you need to do to tell me that I can do that optimization. So it's really the key aspect is not to have an optimization report or a white paper that informs the developer about the cool things to do. It's about the compiler instructing the user to do something very specific, to make some very specific source code changes and check if they are safe to do so, and then enable the optimization that way. And I think this is something that makes our compiler technology even more valuable and gives us more leeway to bring performance to a wide range of applications by simply working and communicating better with the developer. All right, so now with that, I hope I convinced you that we have many nice and interesting toys in our compiler sandbox. So lots of things to play. I think we are creating interesting things. We have many more opportunity. I think the fun doesn't stop. And for this reason, I conclude that the best days for LLVM performance are ahead of us. Thank you.
Thank you, Gerolf. The floor is now open to questions.
Hi. The performance numbers that we saw, those were for AArch64, is that correct?
Yep.
No question on those heroic optimization?
So you mentioned in your, let's see, structs of arrays to arrays of structs. I'm getting it backwards, but you know what I'm talking about here. That when you were looking at the size of struct, you wanted the type information to be available, and I've heard that come up in some other contexts, that the lack of type information can sometimes cause some issues. Do you have any thoughts on how that could be maintained better in LLVM, the type information?
I know that there are considerations along these lines, but I personally did not follow it closely yet. So at this point, it's still very early in what we can do about it. Is it even the right thing to do? I mean, I like it because it helps us to close the gap, the performance gap to our compilers. But it's also an optimization that, if applied blindly, realistically will only help in some benchmark scenarios. So there's a borderline to, call it advanced, to call it heroic. But if we architect it well, and if we create a way for the compiler to communicate that it finds opportunity to apply this optimization and possibly work with the user by maybe having some pragmas or things like that, I think then it goes far beyond the value of improving a benchmark and help a wide range of memory bandwidth bound applications, especially in the server space.
Do you look into code size optimizations? So in most cases, you're focusing on performance. Are you also tracking code size? Any ideas?
So the answer to that is historically no, but that's only part of the answer. Also, I did not really define performance, and it's an interesting question because implicitly from the talk you would assume performance is just runtime performance. As we move forward, the other metrics we will track is compile time, code size, and also the optimization levels. It's right now fairly focused on a benchmark setting. We also want to track, our options, particularly the optimizations for code size in that case, and O2, O3 in a closer way. So yeah, the performance metrics will expand, but we are not quite there yet.
So when you presented the heroic optimization, at the end you said, we can implement all of these transformations. The real hard part is tuning the cost model so it would fire in cases where it's useful. Did you also mean, my naive view would be like also pass ordering there would also be pass ordering problems, like if you have this whole toolbox of potential optimizations, just doing it in the right way, like the way you went through the slides.
Yeah,
you did it in a very particular way. I
Yes.
guess that's actually program specific. Would that also be a problem to solve?
Yes, absolutely. That could be, and that brings up another interesting point because, when you think about pass ordering, what we are doing is just historically, I think what all compilers do is we try to come up with some pass ordering that just applies for all the applications, and you always end up with, these funny dependencies sometimes between the passes, but this is just how compilers have done things historically. As we move forward, we can think of different schemes that if you find some characteristics in functions, you sort of know which optimizations can help, and you can be much more dynamic in the pass ordering somewhere down the road. So,
okay, if you think about it abstractly enough, you could say, oh, that's part of the cost model. Right, okay.
When you were doing your analysis and your evaluation, did you compare with GCC and how that compares? And I'm also curious for your future plans, these heroic optimizations, et cetera. Have you seen if GCC's done the same thing and what their success has been?
No comparison to GCC. One of the reasons is that GCC LTO does not run in our environment.
Actually, adding some comments rather than questions. I think
okay.
When we, because there's quite a bit of question, I think, about cost model, right? How you really do this, right? So kind of share a little bit of our experiences, when we did this, a number of years ago. The way we think about it is that, for example, in the case that you see the most optimization happen there is from loop fusion, right? And you look at two loops, right? You say, well, but I can't really just fuse because I control flow in between, right? And then what kind of optimization I should perform to enable them? And actually, that's how we kind of structure the whole kind of, so it's not really the quantitative cost model say, oh, okay, whether I do this would be beneficial. We actually say that, well, what else I have to do to enable it, right? So in order to do that, I think you have to structure your optimization in a very kind of dynamic way instead of say I have a fixed, sequence of optimization, which is what people typically do. But then that usually, okay, if something hasn't happened, and then when it comes here, you can do loop fusion, okay, tough luck, right? So I think you need to say, okay, what else need to trigger to do that? And that's how we kind of structure and did this before.
So I have a question in the meantime. You mentioned at some point the conditional move issue we have, and you mentioned branch mispredict. So is it a case where the compiler has a choice in the way it will lay out the condition and favoring one or the two other, or the true case or the else case?
Yes, what happens is that the compiler naively combines, whenever it finds the opportunity, it issues the conditional compare, which is essentially combines two branches, and it does so blindly without any information about branch mispredicts. And the bad thing that can happen is that it transfers the branch misprediction behavior from a bad branch to the combined branch.
So is it a case where PGO data would
exactly
help, right?
PGO data or some static information if you see that in the else case or then case you jump to an error function, these standard heuristics.
Yeah.
Have you looked at C++ containers and recommending to users the use of a more efficient container or access patterns into things that would trigger exceptions instead of using just a plain memory?
Yeah, we have not looked into that yet. Do you have any particular?
There are several benchmarks that may
get optimized if you use a plain order.
Okay, that might be a good thing to look at on the PPCook, because this guy is notorious for not moving.
Say again the name of the benchmark.
I don't know.
It's number of C++ benchmarks. There are only a handful in the suites.
Yeah, are you able to say how much you get from PGO compared to just using O3?
From PGO itself, I don't have the numbers on the top of my head right now, but roughly what we see from LTO is somewhere in the 7% to 10% range. And from PGO, I don't have the exact numbers, but I think it's roughly 5%, maybe a bit more. But the optimizations and the gains I mentioned here are independent of PGO and LTO. Sorry, they need LTO, but they don't need PGO. So there's more potential headroom from actually tuning for PGO. We are using LTO and PGO to push the technology. So.
Okay, so I have another question. I don't frequently run spec on my phone, so will those array optimization like structure of array to array of structure or the opposite would help to save my battery life on real-world applications, right?
Right, so this is the thing. It only helps memory bandwidth-bound applications, and that is basically the idea that I bring to the table at the end is so we are doing all these benchmark works, and we're using these benchmarks as proxies for our performance work, and it's a benchmark environment so we can measure it. And the challenge for us is to expand it to the applications. And one of the ideas here is that we need to find ways, first of all, to measure applications. Do they have the characteristic of being bandwidth bound? And then also to enable the compiler to communicate more with the user when this optimization can help. And especially in cases where the compiler is basically almost there to do that transformation or optimization, but it needs a little bit more information from the user to actually do it.
We have 1 minute, the last question. Nobody? So you haven't had the question, so I will ask it for them. But have you tried to run poly on those benchmarks, or are you considering it?
We have not tried it. We went for the incremental approach by looking at the hotspots in the benchmarks. So it's not a decision against poly in any way. But when we find nested loops, loop nests, and we find the use case, we certainly look into it and see what is possible, what is feasible, what makes sense.
Okay. We are out of time. It's time for the break. Thank you for attending.